不能改考题吗？我这要做一些对。等，然后才只用一种类型，这样子不对。
那我等下去找你拿。
我等下刚回去。
就是这个
你在等我。
有异味。
哎，可是没有整个拿过来啊，就没有办法，我的方法。
Okay, so last week we actually established a way to find out possible eigenvalues of a linear operator. So the P is a linear operator on an n-dimensional space V, and V is the basis for V, and A is a metric representation of P relative to the basis. So all this material already know. And so we've shown that lambda is the eigenvalue of P means that it satisfies the eigenequation for some non-zero vector P. Okay. Of course, the V, if this is true, then V is the eigenvector associated with this eigenvalue. If and only that we use the metric representation A, okay, and take the difference. So I is the identity. So this is n times n matrix, and so the identity is n times n identity matrix, and the determinants of this difference matrix we see. So this is we have established. Okay. And a remark to be made here. So let A and A and B matrix represent P suppose that A and D. A is the matrix representation of T, relative basis B for the vector space B, and D is the matrix representation of the same linear operator, relative to another basis C for B. Then A and E are similar, i.e. A can be put with for some invertible matrix. First, P actually is the transition matrix for coordinate transformation. So that would be okay. So we know P actually is the transition matrix from the C coordinate to P coordinate. Okay. Right. So, but the point is A and D are similar. Okay. So they are similar. So then determinant. So A and number I comes to what? Comes to sorry, and P inverse. So we do the substitution, and so we do the substitution here. Because that I is the P inverse. Okay. I inverse, right? So I can put that. And by the product formula for determinant, we have determinant of P, determinant of P minus lambda I, determinant of inverse. Okay, but this is what that this is the inverse of the determinant. So they cancel. So this is determinant. Any questions? So if we use different matrix representation, we use different matrix representation because we can select the arbitrary basis, right, for the vector space B. Okay, and so the matrix representation will change, right, will be different for different bases. But we use the matrix representation, this matrix, to compute the determinants here. You can see that the result will be the same. Okay? Will be the same here. things. Okay? Alright, so now the determinant here is independent of the basis chosen for it. So just show, right? Determinant T minus number I. Just a notation, okay? Because we define determinant only for matrices, but this is linear operator, and I is interpreted as the identity operator. Okay, so this is the So this notation just to tell you that the determinant here, this is actually this determinant. Okay? And here the N is N by N matrix. Okay? So the I is N by N identity matrix here. But this, since this determinant is independent of the basis we choose, so that we just write it down, because that it says that this determinant is just a property of the linear operator. Any questions? Okay, so let's take example. The first example is that so I check the example from textbook. So that there is a basis for the two-dimensional vector spaces R. Okay. Because that we know the scale field. The scale is the set of all real numbers. Okay, so the entries are all real numbers. All right, and so determinant B minus number I I is the determinant of A minus lambda I. Okay. And so that is the determinant 2 minus lambda 1 4 minus 1 lambda. Okay, so this is the determinant. Or I so this is okay, and this is lambda square minus lambda and 6. Right. So that this determinant, which is a polynomial of degree 2, for example. Okay. So that the determinant actually is a polynomial of degree 2 in lambda. Right. By solving the polynomial equation, i.e. we solve okay. And this polynomial can be factorized. Maybe I factorize here. So we can factorize into linear factors. So by solving that, we have lambda equal to 3 or minus 2. That he has 2 eigenvalues. Lambda equal to 3, 3, and then minus 2. So we solve the problem that we find the eigenvalues. Okay, so now to find eigenvectors associated with lambda equal to 3. Okay, so we want to find eigenvectors. We consider the eigenequation P will equal to 3. Okay, so we want to solve this eigenequation. Okay. And this is equivalent to solving so this is going to so A x equal to 3. Right. So x is the coordinate, the b coordinate vector of B. Right? So we solve that. And now we'll consider augmented matrix. So this is equal to right? So because we are solving the homogeneous equation, right? So we don't need to use the augmented matrix. So by row operations, okay. So A minus number I plus 3I. So A is equal to minus 1, 1, and 4, minus 2. Okay. So this is not equivalent to 0 by the replacement. So the kernel consists of okay. So the kernel actually is like this. So any non-zero vector any non-zero vector X is the kernel of A minus 3I is the B coordinate of eigen associated eigen weight. Alright, so in this kernel, the kernel, right, is the B coordinate of an eigenvector 3. So that is 3. Okay, and so if B is say B1, B2, then and X, and the V, okay, is the V1, B coordinate, right? So this is the way we synthesize the B coordinate. And right, so for example, then with 1, okay, then so this is 1, 1, V1 plus right. So this V eigenvector, right? So this is the eigenvector associated eigenvalue 3. Okay, so we find any questions? Because with the measure representation, what we find is just the coordinate vector, right, of eigenvectors. So we have to synthesize it back to a vector in the original vector space. Because vector space V can be very abstract. For example, this could be the space of all polynomials of degree less than or equal to n minus 1. Or we can be the space of continuous functions defined on interval, closed or finite interval, for example from 0 to 1. So the vector space can be very abstract. Okay? Very abstract. And if possible, we can be just a two-dimensional real Euclidean space. This is a very common case. Right? And in that case, the basis can be the standard basis. So if the basis is standard basis, then the coordinate vector is just the original vector, the set. That is very special case, right? That the vector space itself is the Euclidean space itself. And the basis is just the standard basis. In this case, then you have, because this is identity matrix, so the vector is equal to the coordinate vector. Right? So if R2 the B is the standard basis, then we that the same. So the coordinate vector is the original vector the same. This is a very common case, right? The V is just n dimensional Euclidean space. And the basis you choose is the standard basis. Okay? And the matrix representation is just a matrix used to define linear transformation. So in that case, you don't need to synthesize the vector back. You don't need to do that because any vector is just the coordinate vector array relative to the standard basis. Okay, so this is the standard basis for R2. So anyway, you can see that we can, by solving the kernel of this matrix, you can find eigenvectors. So other eigenvectors is just a scalar multiplication of these special vectors. Because it takes the form like this. Eigenvector should be non-zero. Okay, we have to know that. And so we will find the eigenvector. Okay. Similarly, find kernel of A minus minus 2 R. Okay? Corresponding to eigenvector minus 2. And what is that? So this is the for minus 2. So we find that it is okay. So we find this is a square multiplication of 1, 4. So we find that. So that's 1 minus 4. It's the B coordinate of the vector V equal to V1 minus 4 right, so a vector is a big coordinate of an eigenvector. Right? Eigenvector associated eigenvalue minus 2. So for each eigenvalue, we find at least one eigenvector problem. So now we have A, we have A, okay. And let U equal to V1 and the W equal to, right? So we have T U equal to 3U and the T W equal to minus 2W. But by using linear transformation, okay. Right. So U is the, remember, V1, V2 form a basis. Okay. So that we find 3 is an eigenvector, and the U here is an associated eigenvector. And minus 2 is an eigenvalue, and we find an associated eigenvector W, and W is pretty. Because we know they are B coordinates. We know they are B coordinates, so we can synthesize that. Okay. Remember, we define eigenvectors for linear operators. But the technique to find eigenvalue and eigenvector is by using the matrix representation. You know that, right? So matrix is our tool to find eigenvalues of a linear operator and to find eigenvectors of a linear operator. Okay? So the vector, when we found the kernel of them, but in the kernel, if any non-zero common vector in the kernel, it's just the big coordinate. Any questions? So, and now, again, with the matrix. So now, and note that A 1 1 1 4 becomes 2. And such written this way. So that means A. So we form the matrix by using the eigenvectors. So eigenvector 1 1 associated with eigenvalue 3. Put here eigenvectors 1 4, which is the eigenvector associated with eigenvalue -2. Here we find that we have 3 0 0 -2. Okay, so that's A. Okay, so now from here we know A is the matrix representation of T, relative basis. And now we have, and we would like to have this one to be for a certain basis C, right? Because we want to have a matrix representation which is as simple as possible. And we know that diagonal matrix is the most simplest matrix representation for a linear operator. Alright? So we ask for that we want to find a basis C, right? Such that this is the matrix representation. And so in that situation, what is this? This should be a transition matrix for coordinate change. And this should be now here. So with these observations, we are able to find the new basis C. Okay, so this is the right? So what is the basis of C? Here. Okay. So now, so we already find U and W, right? U and W here. And from here, that so with this one, so this implies that with C equal to U and the W, the metric representation of C is just equal to 3, 0, minus 2. Right? So this is the metric representation. So we conclude that the coordinate change is just simple. It's just the so this is U. We know this is U, right? W. Okay. And of course, so this is 1, 1, and 1. So everything just fits to each other, right? So the check-in is that because the transition matrix we studied is this one, right? The basis, the C here, so C is the basis consists of U and W. And it's P coordinate here. So C to B, by our definition of the transition matrix, is so of course fit to. Okay, so now we can find and we can find diagonal metric representation since we can construct the basis C W for V. Consisting of eigen vectors. So the main reason is that we can find, so the main reason to find a diagonal matrix representation of V is because that we can construct a basis C, and this C basis consistent of eigenvectors. So we have to find a basis which consists of eigenvectors. If we can't, if we cannot do this, then we cannot find the diagonal matrix representation. So take the other example. Second example. This time, okay. So the matrix representation is here. And this one. And determinant of A becomes determinant of so that is right. So immediately so we know that E has only one eigenvalue number equal to 2. Right, so T has only one eigenvalue. And our purpose, our goal is to find a basis for the vector space V, right? And this basis consists of 2 eigenvectors. But now, we have only one eigenvalue, right? So we have to find eigenvectors, 2 linearly independent eigenvectors, also associated with the same eigenvalue, because we have only one eigenvector. Okay? So, to be able to find the diagonal matrix representation of B is equivalent to find 2 linearly independent eigenvectors. Okay? To find 2 linearly independent eigenvectors. UW associated so this is the only condition. To find a diagonal matrix representation of T means that we have to construct a basis for V, and this basis consists of eigenvectors only. Okay, and they must be linear independent because they should be form basis, right? So they should be, and because dimension of V is 2, so if we find two linear independent eigenvectors, then we have done. Okay, so this is our purpose. Now, kernel, so we have to solve a minus 2i. Okay, so what is kernel? The kernel of the matrix so this is 0, 1, 0, 0. Okay, so that's kernel. So what is that? It is alright, so all kernels are multiple of 1, 0. So the dimension of kernel is 1. Less than 2. So even though you see that the root of this polynomial it has multiplicity too, right? But the dimension of the kernel is 1 only. Okay. So that is the situation that thus we cannot find two linearly independent eigenvectors associated. Okay, so we cannot find two linear independent eigenvectors associated with eigenvalue. Thus, T right has no diagonal metric representation. Okay. Right. So in this case, that impossible, right, to find the metric representation of T, which is a diagonal matrix. This is the second example. Third example. A so A is here. So the mixed representation relative to a basis is like this one. And so the determinant okay. Right. And so that is my possible. And this is H. There's no real roots. Okay, so there is no real roots. The T has no real eigenvalue. No real eigenvalue. So what is the consequence? No eigenvalues. And so so T, because no real eigenvalues, so of course you cannot find because that things because the scalars is odd, so the coordinate vector should be real vectors. No, because the vector space we consider is a vector space over R, right? So that the coordinate vector should be real vector. Alright? So to have real vectors, and now three coordinates. Okay, so they must be real vectors. But we don't even have a real eigenvalues, right? So that we cannot any diagonal real vector representation. So the reason is that we don't have because we don't have the real eigenvalues. So of course we don't have any diagonal real matrix. Okay. So now let me be a two-dimensional vector space over. So please be a two-dimensional vector space over over C. So the scalar is the set of all complex numbers, and let T be linear. Okay, and we consider it is a linear operator on a two-dimensional vector space over C. So now the scalar can be arbitrary complex numbers, right? And we let A, so let B be a basis for V. And now we let A to be the matrix and permutation of T relative to the basis B, and this is equal to 1, 2, minus 1. So it's the same, right? So we have the same measure representation now here, but the settings are different because in the third example we carry on from the first example that V is a real vector space. Okay, and T is a linear operator on this real vector space, which is two-dimensional. So we select the basis, okay? And the B coordinate would be real vectors because everything is real, right? So the coefficient should be real. Okay, and then we find that we have that the basis we have a real matrix. Okay, the permutations. But once we want to find the eigenvalue, we can't solve, we can't have any real eigenvalue. So we get into trouble. Okay? Because what we want to develop is to find a basis. Right? This basis consists of eigenvectors. And those eigenvectors relative to the basis B should have real coordinates. Alright, so we have to do our problem within the real domain. Everything should be real. So we cannot, even though we know it has complex roots, but we can't use it. We can't. Because we are restricted to the real domain. Everything should be real. Okay. So we get to a deadlock and we say that T cannot have any diagonal real matrix representation. So we have to use real matrix. Because we are talking about the real vector spaces. Now we change the setting. Here, we have a two-dimensional vector space V, but it's over the set of all complex numbers. So the scalar now we talk about is are all possible complex numbers. And the T is the linear operator on this complex vector space. Now, again, that V is a basis for V, okay? And the A now, of course, the basis will be different with that basis. It's just a notation, okay? So that the matrix representation of this linear operator relative to this basis, we assume that we have the same matrix representation. And then determinant A minus lambda I. So again, this is, and so we have So now T has two eigenvalues. I and lambda I. So now we can say that. Now T has two eigenvalues I and minus I. Because we are allowed to discuss, to use the complex number because our scalars are complex numbers. Even though the matrix representation appears as a real, but as you said, this is also a complex matrix, right? Because a real number is also a complex number. Right? So in this case, you should interpret this as a complex matrix. Okay? It's a complex matrix. So now, up to now, before we proceed, the eigen equation, the eigen problem, so you have to know which scalar you are working on. If the scalars should be all real, or it can be complex. If you have to work on the real world, then you have much restriction, just as I illustrated in the third example. Because in that case, in many situations, even if you don't have a real eigenvalue, so you cannot solve the eigenvalue because no real eigenvalue, and you cannot proceed again, right? You cannot. So, but if you are considering complex vector spaces, and you are considering linear operator on complex vector spaces, then algebraically you have no restriction, because every polynomials with complex coefficient can factorize into linear vectors. This is called the fundamental theorem of algebra. Okay. So the fundamental theorem of algebra tells us that any complex coefficient polynomial can be factorized into linear vectors. So that you always has eigenvalue. Okay? You don't have this embarrassed situation in the complex world. You always has eigenvalues. Right? Alright, so now here you have two different eigenvalues now in the complex domain. Okay, so complex world is perfect because in this viewpoint. But even though we have in the complex world we will have eigenvalues, but we will encounter the situation of the second example that we might have enough eigenvectors. If we have eigenvalue with multiplicity bigger than 1. Okay. For example, in this example, we have eigenvalue 2 and its multiplicity is 2. But we can only find one linearly independent eigenvector. We cannot find 2. And the situation will occur in the complex domain. Okay, because I have almost run out of my time. So anyway, so now we can. So I just described because I have no time to proceed to find the kernels, right? So we can find an eigenvector. Say U. sources. Right. Using a non-zero coordinate in the kernel of A minus I. We can also find an eigenvector W associated eigenvalue minus I from a non-zero coordinate in the kernel of A. Alright, so first of all you have to solve for the kernel. You find the kernel because I is already know, we know I is eigenvalue, so the kernel should be non-trivial. So you can always find a non-zero coordinate, means that the non-zero vector here, and you can synthesize to find the eigenvector here. And also here. And so and the C, so that so now this is U and W. So we have U and T W times I W. So the actual representation is relative to these spaces I is 0. So now, of course, the metric representation, which is diagonal, but it is a complex diagonal matrix. Okay? So now you have a complex diagonal matrix representation of T relative to these spaces. So please find the U and the W at home. Okay? Because I have no time to see. But you always can do it. Okay? You can always do it. No problems at all. Okay. And the fifth problem is A. Right. So now we have a complex and determinant. Okay. So we have only one eigenvalue. With multiplicity 2. Alright, so we have multiplicity 2 for the root. And the dimension, you will find that the dimension of kernel of A minus II is only 1, which is less than 2. Okay, so T has no complex diagonal matrix representation. even we are using in the complex domain, we can solve the polynomial equation and we can find eigenvalue. But we still, in this case, we still cannot find two linearly independent eigenvectors associated with the same eigenvalue. You can't still, because the dimension of the kernel is 1 instead of 2. Okay? So in this case, we don't have complex diagonal measure representation. So all these examples, we actually we took 5 examples to illustrate different kind of difficulties when we want to solve the eigenequations. And the purpose at the beginning of the chapter that we would like to find a simplest measure representation for a linear operator. Right? This is our purpose for that. Okay. But this is not always possible. Right? It could be depends on the domain, real domain or complex domain. Okay? Because in the real domain, sometimes we don't even have any real eigenvalue. We don't have eigenvalue. Okay? So we cannot proceed anymore. Even you are in the complex domain, you always have eigenvalue, no problem at all. Okay? But you can't find a basis, right, consisting of eigenvectors. You can't. In this case, you also have no complex diagonal measure value. Okay, so I stop here and start with our quiz.